let's have a look at another group of algorithms that can be auto-vectorized, reduce-like algorithms. The unfortunate thing about reduce is that in order to vectorize it, you need to change the order of operations, right? This is why for floating point, you need to pass fastmask. This is what the codegen looks like with fastmask and without fastmask. And yes, Clang manages to do something, but with fastmask, this is proper vectorization. Now, given that, let's have a look how we can use transform reduce to do certain algorithms. Inner product is perfectly vectorizable, assuming fastmask. A count, if you squinted it, is a reduction, so it can be vectorized. Any, standard any of is not vectorizable by modern compilers. We discussed this when we talked about strlen in C++. However, if we don't stop after we get a match and go to the end, that's vectorizable. The best code gen I've got was with count if. However, like, this is not the best code gen even for this non-stopping loop. Maybe if we try hard enough, we can do better. As well as I suspect that this will be substantially faster if the short circuiting doesn't give you a lot. Finally, my favorite example, minimum value. If you just need the minimum value in the array and you don't care about its position, use standard reduce. This is vectorized and this is crazy faster than min element. I also want to have a look at some other algorithms that will be auto-vectorized, but are not matching neither transform nor transform reduce. Let's start with 4x4 matrices. Right? This is apparently a common enough use case that compiler knows how to vectorize those. Right? This is matrix multiplication, and compiler has vectorized them. Image blend, right? And different operations on like consecutive elements in general, right? But giving two RGBA images, mix them together in a third image, with combining alphas and the channels, right? In this particular case, I'm fairly certain we can do better than what compiler did, but still, nice effort. I also think that this is actually what we saw when we looked at adjacent difference vectorized as adjacent difference and not as transform. So I think that matched this pattern and not transform pattern. GCC has some things that Clang cannot do. At least I couldn't make Clang do them. Converting between arrays of structs and structs of arrays. GCC can vectorize that. GCC can reverse, while Clang can't. So in this video, in order to just for better visuals, I used X86 Assembly because X86 vector instructions are much bigger, like they're just wider than the scalar instructions. However, here I also generated Clang code. You see table. This is table lookup. This is vector instructions. This is rotates one vector, like reverse elements in one vector. And finally, image shuffle, channel image shuffle using Clang. It can do vectorize those, but it thinks that it needs a much more powerful SIMD extension. So this is with AVX512. Okay. Let's briefly mention pragmas. I do not know enough about them, to be honest, but I googled, and I don't believe that with pragmas. You heard that you can vectorize with pragmas. You can tell your compiler, oh, please vectorize this for me. I did not actually see them do anything that we didn't see before. I believe they can do transform and transform reduce, but we can do transform reduce without pragmas. However, they can allow you to tweak your code a little bit, right? So maybe if you need some tuning and you can do it with pragmas, use that. Finally, Microsoft STL. Microsoft decided that on top of vectorizing in the compilers, they're going to vectorize in standard library. Let's see how they did. So first of all, adding up floating point. Like there is no fastmask here. So the regular, if we write it as a loop, right, there is no vectorization. However, standard reduce has special guarantees that, the whole point of standard reduce is that you can add elements in any order, right? And so Microsoft STL authors, they said, we will detect that this is specifically floating point. This is the operation we know, right? And then we will put fastmask on that. And so the standard reduce will be vectorized. And they also did another really nice thing, where for some algorithms, they wrote the vectorization by hand, specifically for standard reverse or standard reverse copy and swap ranges. Right. They wrote the vectorization by hand, and basically, if your type is trivially swappable or trivially copyable or something, they will call the pre-built version. And another thing they did is that everywhere else we were having to test. So basically, the extensions we were using, the SIMD extension we were using, were the ones specified in the compiler options. But here, they do testing at runtime. So even if you don't build with any special compile flags, the implementation at runtime will check which instruction set is available and will use that. Yes, this is overhead on every call, but they decided that this is a better approach, and at least you will get the whole power of vectorization if you have it. And that's it for today.